You are living inside it right now. 1 second, a single tick forward, the time it takes to draw a breath, to blink, to tap your finger once against a table. Ordinary, unmeasurable by feeling. And yet, in the span of that breath, in this second, the one you are inside of at this very moment, more distinct events occur across the universe than there are atoms in all of observable space. More than the grains of sand on every beach, more than the stars you can see, more than every molecule of water in every ocean on Earth, the number of discrete quantum events, particle interactions, photon collisions, and gravitational shifts happening right now, in this single second, exceeds the total count of matter itself by orders of magnitude so vast they break intuition entirely. Let that settle. 1 second. You have lived through billions of them. You will live through billions more if you are fortunate. Each one feels identical, a heartbeat, a breath, a moment of no particular importance. But this second, the one we are inside of together, is not like the others, because we are going to stop. We are going to freeze it, the way a photographer captures a hummingbird mid-flight, wings blurred into invisibility but the bird itself suspended weightless in a single frame. We are going to examine this second the way a jeweler examines a diamond under magnification, turning it slowly, watching the light refract through hidden planes and inclusions. We are going to treat this second not as a sliver of time, not as a subdivision of a minute or a transitional moment between past and future, but as a universe unto itself, vast, populated, and as worthy of exploration as the 13 billion years that came before it. This is a journey outward and inward, across scales so enormous and so small that language begins to fail. We will move from the human body, your heartbeat, your breath, your perception, outward to the surface of distant stars, to galaxies pulling away from one another at the edge of visibility, to the birth and death of suns happening in clusters too far away to name. And then we will return. We will descend past the cell, past the molecule, past the atom, into the subatomic storm where particles flicker in and out of existence, where time itself becomes elastic, where a second is not a second at all, but a canvas stretched across trillions of micro-events, each one as real and as consequential as the beat of your heart. If this is the kind of thing that pulls you deeper, if you find yourself drawn to the strangeness hiding inside the familiar, to the quiet vertigo of scale, to the places where the universe stops making intuitive sense and starts making a different, harder kind of sense, then stay. There's a great deal waiting here, and if you would like more of this, if you want to be reminded when the next journey begins, the button is there. You know where it is. Now, let us begin. Let us start with you, with your body, with the thing you know best, the thing you have lived inside of every day of your life, the thing that has accompanied you through every second you have ever experienced. Because the second you are living in right now is not an abstraction. It is not a number, not a definition, not a concept held at arm's length. It is a physical event, happening in tissue and blood and electrical current, happening in the chambers of your heart and the neurons behind your eyes. You're not observing the second, you're inside it. You're made of it. Picture your heart. Not the metaphorical heart of poetry or greeting cards, but the actual organ, a fist-sized muscle locked inside your ribcage, tethered by veins and arteries, suspended in a sack of thin membrane. It is beating right now. You do not have to think about it. You cannot stop it by willing it to stop. It moves on its own, driven by a cluster of cells no larger than a grain of rice, buried in the upper wall of the right atrium. This is the sinoatrial node, your body's pacemaker. It fires on its own rhythm, a self-sustaining electrical pulse that ripples outward through the muscle, triggering contraction, triggering release, triggering the movement of blood. At a resting heart rate of 75 beats per minute, your heart completes one full cycle in exactly 8/10 of a second. Not 1 second, slightly less. The math is simple. 60 seconds divided by 75 beats, 0.8, 800 milliseconds, which means that a single second, the second we are examining, the second we have frozen and placed under the lens, is actually slightly longer than one heartbeat. It contains one beat and then a fractional pause, a moment of diastole, of rest before the next beat begins. What happens in those 8/10? The sinoatrial node fires. The electrical impulse spreads across the atria, the two upper chambers, causing them to contract. Blood is pushed downward into the ventricles, Then the impulse reaches the atrioventricular node, a second cluster of specialized cells, and it pauses. For 1/10 of a second, the signal is delayed. This is deliberate. This is necessary. The delay gives the atria time to finish emptying, gives the ventricles time to fill completely before they are asked to contract. After the delay, the signal races down through the bundle of His, through the Purkinje fibers, and into the thick, muscular walls of the ventricles. They contract, hard. Blood is forced upward, out through the aortic and pulmonary valves, into the arteries, into the lungs, into the body. This is systole. It lasts 3/10 of a second. Then comes diastole. The chambers relax, the valves close, blood flows back in from the veins, and the cycle resets. Diastole lasts 5/10 of a second, longer than systole because the heart needs more time to fill than it needs to empty. The second heart sound, the one doctors listen for with a stethoscope, the one you hear as a dull thud if you press your ear to someone's chest, is the sound of the aortic and pulmonary valves snapping shut at the beginning of diastole. That sound is the heart sealing itself, preparing for the next beat. In 1 second, this happens once, completely, perfectly, autonomously. Your heart does not consult you. It does not wait for permission. It beats because the cells that make it beat are designed to fire, to pulse, to keep time. And they do. They will for decades, for 70 or 80 or 90 years, without Shusi, without pause, until the day they don't. Now consider what you're seeing, right now. The light entering your eyes, the words you are reading or the voice you're hearing, the room around you, the screen in front of you. It feels immediate. It feels like now. But it is not. By the time your brain has assembled the image, has processed the photons striking your retina, has interpreted the signals sent from your eyes through the optic nerve to the visual cortex at the back of your skull, time has passed. Not much, but enough. The retina receives light near instantaneously. Photons hit the rods and cones, specialized cells that convert light into electrical signals, and those signals begin their journey inward. But the brain is slow. Relative to the speed of light, relative to the speed of the signals themselves, the brain is sluggish. Studies have measured visual processing latency, the time it takes for the brain to recognize a simple image, at anywhere from 13 milliseconds for rapid categorization to over 100 milliseconds for complex perception. 100 milliseconds, 1/10 of a second. What this means is that you are always living in the past, not the distant past, not the past of memory or nostalgia, but a fractional past, a delay so brief you would never notice it under normal circumstances, but a delay nonetheless. When you see something happen, a light turning on, a hand moving, a face turning toward you, you are not seeing it in the moment it happens. You're seeing it 1/10 of a second later. Your brain is showing you a reconstruction, a model of reality assembled from delayed signals. The light has already bounced, the hand has already moved, the face has already turned, and only now, after the delay, after the processing, do you perceive it. The psychologist William James had a name for this. He called it the specious present. The word specious here does not mean false, though it carries that connotation. It means something closer to deceptive, or misleading, or constructed. James was writing in 1890 in his monumental work The Principles of Psychology, and he was trying to articulate something that had bothered philosophers for centuries: the nature of now. What is the present moment? How long is it? If time flows continuously, if every instant is immediately replaced by the next, then how can we experience anything at all? How can we hold a melody in our heads, or follow a sentence, or perceive motion, if each individual moment is gone before we can register it? James argued that the present is not a knife edge. It is not an infinitesimal point between past and future. It has breadth. It has duration. He described it as a saddleback, a stretch of time within which sensory information is integrated into a single coherent experience. The specious present, he suggested, could last as long as 12 seconds, though modern research has narrowed that estimate considerably. Most psychologists now agree that the felt duration of now, the window within which you experience events as simultaneous, as part of the same moment, lasts roughly 2 to 3 seconds. Let that sink in. A single second is shorter than your conscious experience of the present. When you think about now, when you feel the immediacy of this moment, you're not feeling 1 second. You're feeling 2 or 3 blurred together, overlapping, integrated into a single perceptual window. A second by itself is too brief. It slips past unnoticed, indistinguishable from the second before it or the second after. It is only when we accumulate 2 or 3 of them, only when we gather them into a small bundle of time, that we begin to feel the texture of experience. And yet, inside that single second, the one we have frozen, the one we are examining, your heart has beaten once. Your eyes have sampled the world at least 10 times, in discrete bursts of neural activity tied to alpha oscillations in the visual cortex. Your lungs have expanded or contracted, depending on where you are in the breathing cycle. Your blood has moved. Your neurons have fired. Your body has done thousands of things quietly, automatically, without you noticing. This is the human second. This is the warm, intimate, familiar second. The one you know, the one you live inside of, the one that feels unremarkable because you have never had reason to examine it closely. But we are not staying here. This is the departure point. This is where the journey begins. Because the second you are living in, the second your body is experiencing right now, is also being lived by the rest of the universe. And out there, beyond your heartbeat, beyond your breath, beyond the walls of the room you're sitting in, the second is doing something else entirely. Before we leave, though, we need to ask a harder question. A foundational question. One that sits underneath everything we're about to explore. What is a second? Not what does it feel like? Not what does it do? But what is it precisely? How do we know when a second has passed? How do we measure it? How do we define it? For most of human history, the answer was simple. A second was 1/60th of a minute, which was 1/60th of an hour, which was 1/24th of a day. The day was the thing we measured against. The rotation of the Earth, the movement of the sun across the sky, the cycle of light and dark. A second was just a subdivision of that cycle, a convenient unit, a way to break the day into smaller, more manageable pieces. But the Earth is not a perfect clock. Its rotation slows over time imperceptibly as tidal forces from the moon transfer angular momentum and the planet gradually loses energy. The length of a day changes, not by much, fractions of a millisecond per year, but it changes. And if the day changes, then the second changes, which means the second was not a constant. It was a variable. It drifted. This was a problem. By the middle of the 20th century, as technology advanced, as timekeeping became critical for navigation and communication and scientific research, the drifting second became intolerable. Physicists needed a standard that did not drift. They needed a second that was the same today as it was yesterday, as it would be tomorrow, as it would be 1,000,000 years from now. They needed a second rooted not in the motion of the Earth, but in something deeper, something more fundamental, something that could not change. They found it in the atom. On October 13th, 1967, at the 13th General Conference on Weights and Measures in Paris, France, the second was redefined. The resolution, adopted by delegates from across the world, abrogated all previous astronomical definitions. The second was no longer tied to the Earth. It was no longer tied to the Sun. It was tied instead to the behavior of a single element, cesium-133. The new definition was precise, exact, unambiguous. The second is the duration of 9,192,631,770 oscillations of the radiation corresponding to the transition between the two hyperfine levels of the ground state of the cesium-133 atom. Read that again, slowly. 9,192,631,770. Not 9 billion, not approximately 9 billion. Exactly that number, that specific count of oscillations, every second, everywhere, for all time. This is not a metaphor. This is not a convenient approximation. This is the definition. A second is not a feeling. It is not the time it takes your heart to beat, or the time it takes to snap your fingers, or the time it takes light to travel a certain distance. It is the time it takes a cesium atom, isolated and unperturbed, held at absolute zero, to oscillate exactly that many times. The choice of cesium was deliberate. Cesium-133 is stable. It does not decay. It does not change over time. And its hyperfine transition, the specific energy shift of its outermost electron when it flips between two quantum states, occurs at a frequency that is extraordinarily sharp, extraordinarily consistent and extraordinarily measurable. The radiation emitted during that transition falls in the microwave range, at a frequency of just over 9 GHz. It is easy to detect, easy to count, easy to reproduce. At the National Institute of Standards and Technology in Boulder, Colorado, in a windowless laboratory surrounded by foothills and mountains, there is a machine that counts these oscillations. It is called NIST F2, a cesium fountain atomic clock. The clock does not tick. It does not have hands. It has no moving parts in the conventional sense. Instead, it uses lasers to cool cesium atoms to a few millionths of a degree above absolute zero, then tosses them upward in a vacuum chamber where they arc through the air like a fountain, passing through a microwave cavity tuned to the exact frequency of the hyperfine transition. The atoms absorb the microwaves. They flip states, and the machine counts the flips. NIST F2 is accurate to within 1 second per 300 million years. If you started it at the moment the dinosaurs died 66 million years ago, and let it run continuously until today, it would be off by less than a quarter of a second. Its predecessor, NIST F1, operational since 1999, was accurate to within 1 second per 100 million years. These are not clocks in the way you think of clocks. They are quantum instruments. They are measuring the fabric of time itself, using the behavior of atoms as a ruler. This is unsettling. Stop and feel the weight of it. The most intimate unit of time in your life, the second, the thing you use to time your coffee, to count down to midnight, to measure how long it takes to fall asleep, is not rooted in anything human. It is not rooted in the stars. It is rooted in the quantum behavior of a single isotope of a single element, an isotope that has no particular significance to your body, or to the Earth, or to the solar system. Cesium-133 was chosen because it was convenient, because it worked, because the transition was clean and the frequency was stable and the measurements were repeatable. There is something profound in that, something almost poetic, though the poetry is cold. The French foreign minister at the time of the 1967 conference reportedly remarked on the strangeness of measuring the stars, measuring time itself, based on the oscillation of an infinitesimally small atom. It is backwards, in a way. For all of history, we measured time by looking up, by watching the sun rise and set, by tracking the moon's phases, by charting the slow procession of constellations across the night sky. We measured the large by the large, but now we measure the large by the small. We measure the cosmos by the atom. We look inward to understand outward, and the atom does not care. The cesium atom in the NIST F2 clock has no awareness of what it is being used for. It does not know it is keeping time for GPS satellites, for cellular networks, for power grids, for the entire infrastructure of modern civilization. It oscillates, because that is what it does. That is what the laws of physics require it to do. It flips between quantum states at a fixed frequency, the same frequency it has always had, the same frequency it will always have, until the end of time. This is the foundation. This is the bedrock. Before we go any further, before we step outside the human body and into the wider universe, we need to hold this truth. The second is not ours. It never was. We borrowed it from the atom. We built our lives around it, our schedules, our calendars, our entire experience of duration. But the second belongs to cesium. It belongs to the quantum world. It belongs to the deep structure of matter, to the rules that govern how electrons can exist and what states they can occupy, and how energy moves between them. When we talk about a second, this second, the one we have frozen, we are talking about 9 billion oscillations of a cesium atom. We are talking about a number so large it loses meaning when spoken aloud, a number that takes longer to say than the duration it describes, and yet that number is precise. It is fixed. It does not drift. It does not change. Out there, in Boulder, the fountain clock is running. The cesium atoms are arcing through the vacuum. The lasers are cooling them, the microwaves are probing them, the detectors are counting the flips, and the number climbs. 9 billion, then 9 billion again, then again. Over and over, second after second, the same count, the same oscillation, the same quantum heartbeat. This is the second you are living in. This is the second we are about to explore. Not the human second, not the second of heartbeat and breath and perception, but the atomic second, the quantum second, the second that exists whether you are here to feel it or not. And now that we know what it is, now that we have defined it, pinned it down, locked it into place with the precision of 9 billion oscillations, we can begin to ask the real question. What else is happening right now in this single second? Your heart has beaten. Your eyes have sampled the world. Your neurons have fired. But those are local events, small events. Events confined to the 3 pounds of tissue inside your skull and the few litres of blood circulating through your body. The second we're inside of is not confined. It is universal. It is happening everywhere, all at once. On the surface of the sun, in the core of distant galaxies, in the space between stars, in the empty void at the edge of visibility. And if we want to understand it, if we want to see it the way the cesium atom sees it, as a fixed duration within which an almost unimaginable number of things happen, then we need to step outside. We need to leave the warmth of the human body behind and move into the cold, into the vastness, into the places where a second is not a heartbeat but a storm, not a breath but a flood, not a moment of rest but a cascade of events too numerous to count, too fast to track, too strange to fully comprehend. We will return to the body. We will return to the brain, to the heartbeat, to the lag between seeing and perceiving. But not yet. First, we go outward. First, we see what the universe is doing in this second, the same second you're living in right now, the same second the cesium atom is oscillating through in a laboratory in Colorado. The journey begins here, at the edge of the familiar, at the threshold where the human second gives way to something larger, something colder, something that does not care whether you are ready or not. The planet beneath us is not still. Earth, from a distance, appears serene. A blue marble suspended in the void, clouds tracing slow arcs across its face, continents fixed in place. But zoom closer, descend through the atmosphere. Watch the surface in real time, compressed into the span of a single second, and the illusion of stillness collapses. The planet is thundering, it is gestating, it is scarred by light and heat and the constant grinding movement of rock against rock. In this second, our second, the one we have frozen, Earth is not resting, it is working. Start with the lightning. Somewhere over the Atlantic, a cumulonimbus cloud towers 12 kilometers into the sky. Inside it, ice particles collide. Positive charges rise, negative charges sink. The separation builds until the air itself can no longer resist. A channel opens, electrons pour downward at a third the speed of light, ionizing a path from cloud to ground. The lightning bolt you see, the brilliant branching scar across the sky, is not the initial discharge. It is the return stroke, the surge of current racing back up the ionized channel, heating the air to 30,000 degrees Celsius in less than a millisecond. The air explodes outward. You hear it as thunder. In 1 second, this happens approximately 100 times across the surface of the planet. Not in one place, everywhere. Over the Amazon basin, over the Congo, over the Indian Ocean, over the Great Plains of North America, lightning does not pause. It does not take a breath. The planet's atmosphere is a constant engine of charge separation and discharge, a global circuit that never switches off. 100 bolts in 1 second, 100 channels of superheated plasma connecting sky to earth, 100 cracks of thunder radiating outward through the air. Let that settle for a moment. 100 lightning strikes, not in an hour, not in a minute. In the span of time it takes your heart to beat once. Now shift your attention south, to the Amazon basin, to the green lung of the planet, the forest that stretches across 9 countries and holds more plant biomass than any other terrestrial ecosystem on Earth. The Amazon is often spoken of as a carbon sink, a vast repository where trees pull carbon dioxide from the atmosphere and lock it away in wood and soil. But the truth is more complicated. The forest is a dynamic system. It breathes in and it breathes out. It absorbs carbon and it releases carbon. And in this second, the balance is shifting. The trees are still pulling. Root hairs in the soil are still drawing water upward. Stomata on the underside of leaves are still opening, still allowing carbon dioxide to diffuse inward toward the mesophyll cells where photosynthesis occurs. Chloroplasts are still splitting water molecules, still stripping electrons, still building sugars from carbon and light. In 1 second, across the entire Amazon basin, the forest absorbs roughly 2.4 million kilograms of carbon dioxide. That is the mass of 2,000 compact cars vanishing from the air and into the wood of trees in the time it takes you to say the word now. But the forest is also burning, it is being cut. In some regions, particularly the southeastern Amazon, the balance has tipped. More carbon is leaving than arriving. The sink has become a source. Fire releases carbon in minutes that took decades to sequester. Deforestation opens the canopy, dries the soil, and shifts the microclimate in ways that make further burning more likely. The Amazon is not one thing. It is a patchwork of health and degradation, of growth and loss, all happening at once, all compressed into the same second. Beneath the forest, beneath the ocean, beneath the lightning-scarred surface of the planet, something even slower is moving. The crust itself. The rigid shell of rock on which everything rests is not rigid at all. It floats. It drifts. It grinds against neighbouring plates in a process so gradual that no human has ever felt it in real time. And yet, it never stops. Tectonic plates move at speeds measured in centimetres per year. The Pacific Plate, one of the fastest, advances roughly 10 centimetres annually, about the rate at which your fingernails grow. That is a speed so slow it defies intuition. But we are not measuring years, we are measuring 1 second. And in 1 second, the Pacific Plate moves approximately 1 nanometer, 1 billionth of a meter, a distance smaller than a virus, smaller than a wavelength of visible light. The plate advances this distance while you read this sentence, and the sentence after, and the one after that. It does not stop. It does not pause. It drifts, molecule by molecule, through a second that feels frozen to you. But the consequences of that drift are not frozen. Somewhere, deep in the crust, a fault line has been locked for decades. Stress has been building. The rock is bending, compressing, storing energy the way a drawn bow stores energy in its limbs. And then, without warning, it breaks. The fault slips. The stored energy releases in a single, catastrophic rupture. Seismic waves radiate outward in all directions, travelling through solid rock at 8 kilometers per second. In 1 second, those waves have already travelled 8 kilometers from the epicenter, fracturing through the mantle, bending around the planet's core, arriving at seismometers on the opposite side of the world within minutes. The earthquake you feel is not the rupture itself. It is the wave, the echo, the energy passing through you, shaking the ground beneath your feet, toppling buildings, opening cracks in pavement, all because a plate moved 1 nanometer too far, and the rock could no longer hold. Now, look up. Look at the sky. In this second, across the planet, 4 to 5 human beings are born. 4 to 5 new lives begin. 4 to 5 hearts start beating for the first time. The number varies depending on the data set, on the method of real-time population modelling, on the assumptions baked into the algorithms that track births and deaths across 7 billion people. But the order of magnitude is stable, 4 to 5 per second. That is roughly 360,000 births per day, 130 million per year, a newborn every quarter second somewhere on the planet, entering a world of lightning and carbon and grinding rock. And in the same second, approximately 2 people die. 2 hearts stop, 2 brains go dark, 2 lives conclude. The ratio is not equal, births outpace deaths. The population is still growing, but the gap is narrowing. Within your lifetime, the global death rate will match the birth rate, and the human population will peak, plateau, and begin to decline. But that is decades away. In this second, the planet is still gaining people. 4 to 5 arrive, 2 leave. The net change is positive. Think about what that means. In the span of time it takes cesium to oscillate 9 billion times, 4 new human beings have taken their first breath. 2 have taken their last. Lightning has struck the surface 100 times. The Amazon has pulled 2.4 million kilograms of carbon from the air. Tectonic plates have advanced by nanometers. Seismic waves have travelled 8 kilometers through the mantle. The planet is not a backdrop. It is not a stage on which life performs. It is a participant. It is alive in its own way, for not conscious, not aware, but active, dynamic, never resting, not even for a second. This is the Earth-scale second. The second of geology and atmosphere and the slow churn of carbon and rock. But life does not stop at the planetary scale. Life operates at a dizzying range of speeds, each one tuned to survival, each one shaped by evolution over millions of years. And some of those speeds are so fast, so extreme, that they make the lightning look slow. Consider the peregrine falcon. High above the ground, perhaps 2,000 meters up, a falcon spots a pigeon. The decision is made instantly. The falcon folds its wings tight against its body, tucks its talons, and drops. This is not a glide, this is a stoop, a controlled fall. The falcon accelerates under gravity, but it is not passive. It adjusts the angle of its body, the position of its wings, the tilt of its head. Air rushes past at speeds that would shred an unprotected surface. The falcon's nictitating membrane, a translucent third eyelid, slides across its eye to shield it from debris. Bony tubercles inside its nostrils baffle the incoming airflow, preventing the falcon's lungs from collapsing under the pressure. At terminal velocity, the peregrine falcon reaches speeds exceeding 320 km per hour. Some estimates, based on instrumented flights using captive birds, push the record higher, 389 km per hour, documented in 2005 by researcher Ken Franklin using a falcon named Frightful, equipped with a body-mounted flight computer, that is 308 meters per second. In our second, this frozen second we are exploring, a falcon in full stoop covers 22 meters. It falls the length of a 6-story building. It closes the distance to its prey by a margin that the pigeon, with its slower reaction time, cannot compensate for. The strike is over before the pigeon knows it has begun. Now shift scale, shrink down, watch the hummingbird. A rufous hummingbird hovers in front of a flower, its wings a blur. You cannot see the individual beats, your eye is too slow, but the wings are not stationary. They are rotating in a figure-8 pattern, pushing air downward and backward on both the forward stroke and the return stroke. This is not the simple up-down flapping of most birds. This is something more complex, more energetically expensive, more precise. The hummingbird's shoulder joint is a ball and socket, allowing rotation in nearly every direction. The wings beat at 80 times per second. In our second, the wings have completed 80 full cycles, 80 figure-8s, 80 pulses of air pushed downward to keep the bird suspended in space, motionless relative to the flower, while its tongue darts in and out, licking nectar at a rate of 13 times per second. The hummingbird's heart is beating at 1,263 times per minute. That is 21 beats per second. In the time it takes your heart to beat once, the hummingbird's heart has beaten 21 times. Its metabolism is so high that it must consume more than its body weight in nectar each day. At night it enters a state called torpor, a controlled hypothermia, because it cannot sustain this metabolic rate without constant feeding. The hummingbird lives fast. It burns fast. It operates on a timescale so compressed that a single second is not a moment. It is a marathon. Now, shift again. To the cheetah. The cheetah is already at full sprint. Its spine flexes and extends with each stride, lengthening its reach, compressing and releasing like a spring. Its claws are semi-retractable, providing traction. Its tail swings behind it, a counterbalance, a rudder. The cheetah is the fastest land animal on Earth, capable of reaching speeds of 112 kilometers per hour, that is 31 meters per second. In our second, the cheetah has covered 31 meters. It has closed the gap between itself and the fleeing gazelle. The chase is almost over. The cheetah's lungs are screaming. Its body temperature is rising toward dangerous levels. It can sustain this speed for only a few more seconds before it must stop, panting, overheating, risking collapse. But in this second, it is still running, still closing, still fast. And then there is the mantis shrimp. The mantis shrimp is small. It lives in burrows on the ocean floor. It has compound eyes more complex than any other animal, capable of perceiving polarized light and a spectrum of color far beyond human vision. But the mantis shrimp is not known for its eyes. It is known for its strike. The mantis shrimp's raptorial appendage, a club-like limb folded beneath its body, is spring-loaded. Muscles contract, storing energy in a saddle-shaped structure made of compressed chitin and protein. The appendage is held in place by a latch. When the latch releases, the appendage accelerates from 0 to 23 meters per second in 2.7 milliseconds. That is faster than a bullet fired from a low-caliber handgun. The acceleration is so extreme that it exceeds 10,000 times the force of gravity. The strike itself is devastating, capable of shattering the shells of snails, crabs and clams with a single blow. But the strike is not the only weapon. The speed is so great that it creates cavitation bubbles in the water, vapour-filled pockets that collapse almost instantly, producing a secondary shockwave, a burst of heat, and even a flash of light. The prey is hit twice, once by the appendage and once by the collapsing bubble. Both impacts occur within a few milliseconds. Both occur within the span of 1/100th of a second. The mantis shrimp strike is over before most animals can register that it has begun. And then there is the blue whale. The blue whale is the largest animal ever to have lived, larger than any dinosaur. A blue whale's heart weighs 200 kilograms. It is the size of a small car. You could crawl through its aorta, and that heart beats slowly, very slowly. Research published in 2019 by biologist Jeremy Goldbogen and his team tracked the heart rate of a blue whale using a suction cup electrocardiogram tag attached to the whale's body near Monterey Bay, California. The whale was a 15-year-old male. The tag stayed attached for several hours, recording the whale's cardiac rhythm as it dove, fed and surfaced. The results were striking. At the surface, the whale's heart beat 25 to 37 times per minute. That is roughly one beat every 2 seconds. During deep foraging dives, the heart rate dropped to as low as 2 beats per minute. 2 beats in 60 seconds. 1 beat every 30 seconds. In our second, the blue whale's heart is coasting. It is between beats. The chambers are filling. The valves are closed. The muscle is resting. The whale is gliding through the water, its massive body displacing hundreds of tons of seawater, its flippers adjusting slightly to maintain course. The heart will beat again, but not yet. Not in this second. In this second, the whale is holding, suspended between one beat and the next. These are the speeds of life. The falcon drops 22 meters. The hummingbird beats its wings 80 times. The cheetah covers 31 meters. The mantis, shrimp, fires its strike in less than 3 milliseconds. The blue whale drifts between heartbeats. All of this is happening in the same second. The same frozen span of time, the same 9 billion cesium oscillations. Evolution has tuned each creature to its own rhythm, its own time scale, its own way of moving through the second. There is no single speed of life. There is only a spectrum, a range so vast that the fastest and the slowest occupy different universes, perceiving time in ways so different that they might as well be living on different planets. The falcon perceives the world in sharp, rapid frames. Its vision is faster than yours. It sees details you cannot. It reacts to changes in motion that your brain would smooth over, average out, ignore. The mantis shrimp strike is faster than the mantis shrimp's own nervous system can process. The strike is not aimed. It is pre-aimed, preloaded, pre-decided. The shrimp positions its body, locks the target, and releases. The strike happens faster than feedback, faster than correction, faster than thought, and the blue whale, coasting between heartbeats, is not experiencing the second the way you are. For the whale, this second is a long, slow glide, a quiet moment, a pause in the rhythm. The whale does not rush, it doesn't need to, its size protects it. Its metabolism is slow because it can afford to be slow. There is no predator large enough to threaten an adult blue whale. There is no need for the explosive speed of the cheetah or the rapid-fire wing beats of the hummingbird. The whale moves through time at its own pace, and that pace is glacial. This is what the second contains. Not one speed, not one rhythm, but all of them. The lightning strike and the tectonic drift. The falcon's stoop and the whale's glide. The hummingbird's wing beat and the mantis shrimp's cavitation bubble. The heartbeat of a newborn baby and the final breath of someone dying. All of it layered into the same span of time. All of it happening at once. Everywhere. In the single second we have chosen to freeze and examine. And this is still just the surface. This is still just the planetary scale, the biological scale, the scale of things you can see and touch and measure with instruments designed for human hands. We have not yet left the Earth. We have not yet looked up at the sun. We have not yet ventured into the places where a second is not a heartbeat or a lightning strike, but something stranger, something faster, something that operates on timescales so compressed that the word second begins to lose meaning. But we will. We are building toward it. We are moving outward, step by step, scale by scale, From the cesium atom to the human heartbeat to the falcon stoop to the tectonic drift to the lightning storm. Each step takes us further from the familiar. Each step shows us that the second is not one thing. It is a container, a frame, a window through which we can see the full range of speeds at which the universe operates. The Earth is not still, life is not slow, and the second, this second, the one we're inside of us, is not empty. It is full, over full, crowded with events, layered with processes, alive with motion and change and the constant, relentless churn of matter and energy and time. Let that settle. Let it sink in. The second is not yours. It is not human-sized. It is universal, and we have only just begun to see what it contains. But here is the part that complicates everything we have just built. Here is the place where the second, your second, the one you feel passing right now, begins to unravel. You're not experiencing this moment. Not this one. Not now. You're experiencing a moment that already ended roughly half a second ago. Your brain is showing you an edited recording, a delayed broadcast, a reconstruction of events that have already occurred. The present moment, the one you believe you are living inside of, is a lie your neurons are telling you. A beautiful, necessary, completely unavoidable lie. Let me show you why. Right now, as you listen to these words, your brain is processing approximately 100 trillion synaptic events per second. 100 trillion. That is the number of connections, synapses, firing, signaling, passing chemicals and electrical charges between the 86 billion neurons in your skull. Each neuron can fire up to 100 times per second. Some fire faster, some slower, but the average is somewhere in that range, and when you multiply it out, 86 billion neurons, each connecting to thousands of others, each firing dozens or hundreds of times per second, you arrive at a staggering number, a number so large that it is difficult to hold in your mind. Your brain, in 1 second, performs more operations than all the computers on Earth combined performed in the year 1990. And yet your conscious awareness, the part of you that feels like you, the part that experiences the second as a lived moment, processes information at a rate of roughly 10 bits per second. 10. Not 10 trillion. Not 10 billion. 10. That is the speed of human thought. That is the bandwidth of consciousness. You're taking in sensory information at a rate of 1 billion bits per second. Light hitting your retinas, sound waves vibrating your eardrums, pressure sensors in your skin firing constantly. And your conscious mind is processing 10 bits of it. 10 bits per second. The rest is filtered, discarded, compressed, summarized, or handed off to unconscious systems that handle it without ever telling you. You're not aware of most of what is happening to you. You cannot be. There is not enough bandwidth. There is not enough time, and even those 10 bits per second are delayed. In 1983, a neuroscientist named Benjamin Libet ran an experiment that has troubled philosophers and neuroscientists ever since. The setup was simple. Libet asked volunteers to perform a simple task: flex their wrist whenever they felt like it. No external cue, no countdown, just wait until the urge arises and then move. While they did this, Libet measured 2 things. First, he measured the exact moment when the brain's motor cortex began preparing for the movement, a signal called the readiness potential, visible on an EEG as a slow-rising wave of electrical activity. Second, he asked the volunteers to report the exact moment when they became consciously aware of their intention to move. He gave them a clock with a fast-moving hand, and they noted where the hand was when they felt the decision form. The results were unsettling. The readiness potential, the brain's preparation for movement, began roughly 350 to 500 milliseconds before the volunteer reported any conscious intention to move. The brain was already preparing the action, already building the motor command, already setting the muscles in motion, and the person, the conscious person, the one who believed they were making the decision, did not know about it yet. They would find out half a second later when the brain finally informed them that a decision had been made. The implication is this: your brain decides, and then, after a delay, it tells you that you decided. It gives you the experience of willing an action that has already been set in motion. You feel like you're driving, but you're actually watching a recording of someone else driving, and that someone else is you, half a second ago. This is not a flaw. This is not damage. This is how the system works. This is what it means to be conscious. Your sensory systems are fast. Your unconscious processing is fast. Your reflexes, your motor planning, your threat detection, your pattern recognition. All of these run in real time, or close to it. But your conscious awareness, the part that narrates your life to you, the part that feels like it is making decisions and experiencing the world, is slow. Deeply, unavoidably slow. It lags behind reality by hundreds of milliseconds, and sometimes more. Consider a professional baseball player, a hitter standing at home plate, bat in hand, watching a pitcher wind up and release a fastball. The pitch comes in at 95 miles per hour. The distance from the pitcher's mound to home plate is 60 feet 6 inches. The ball covers that distance in roughly 400 milliseconds, less than half a second. You have 400 milliseconds to see the ball, identify its speed and spin and trajectory, decide whether to swing and execute the swing. But you cannot do all of that in 400 milliseconds, not consciously. It takes approximately 100 milliseconds for light from the ball to hit your retina, travel through the optic nerve, and reach the visual cortex at the back of your brain. Another 100 milliseconds, give or take, for that visual information to be processed, interpreted, and sent forward to the motor cortex. Another 25 milliseconds for the motor command to travel from your brain, down your spinal cord, and out to the muscles in your arms and shoulders. Another 150 milliseconds for those muscles to contract and complete the swing. Added up. 100 plus 100 plus 25 plus 150. 375 milliseconds. That is the absolute minimum time required for your brain to see the ball, decide to swing, and execute the swing. And that leaves you with only 25 milliseconds, a 40th of a second, to assess the pitch and decide whether to commit. Except it is worse than that, because those numbers assume perfect conditions, no hesitation, no second guessing, no conscious deliberation. The moment you try to think about it, the moment you try to consciously decide whether the pitch is a strike or a ball, high or low, inside or outside, you have already lost. The ball is past you. You have missed. A professional hitter does not consciously decide to swing. They cannot. There is not enough time. Instead, they rely on something else. Pattern recognition, unconscious prediction. The brain, without asking permission, identifies the pitcher's release point, the spin of the ball, the angle of the seams, and makes a guess, a very fast, very educated guess, about where the ball will be in 400 milliseconds. And then the brain initiates the swing and the body executes it. And only after the swing is already in motion does the conscious mind catch up and experience the decision as though it had been made deliberately. Mickey Mantle, one of the greatest hitters in baseball history, once tried to explain what it felt like. "I never really could explain it," he said. "I just saw the ball as big as a grapefruit." He did not say he thought about it. He did not say he calculated. He said he saw it. The ball looked bigger, clearer, slower than it should have. His unconscious brain was feeding him a simplified, enhanced version of reality, a version his conscious mind could hold on to long enough to feel like he was in control. Ted Williams, another legendary hitter, put it differently. "Baseball is the only field of endeavor," he said, "where a man can succeed 3 times out of 10 and be considered a good performer. 3 out of 10. That is the success rate of the best hitters who ever lived. 70% of the time they fail, not because they are not skilled, not because they are not fast, but because the task is impossible. Because 400 milliseconds is not enough time for a conscious mind to see, decide, and act. The only way to succeed even 30% of the time is to bypass consciousness entirely. To let the fast systems handle it. To trust the lag. And this lag, this half-second delay between event and awareness, is everywhere. It is not unique to baseball. It is not unique to high-speed athletics. It is the texture of your entire life. You are listening to these words. You believe you are hearing them now, in this moment, as they are spoken. But you are not. The sound waves reached your eardrums a few milliseconds ago. The cochlea transduced them into electrical signals a few milliseconds after that. The auditory cortex processed those signals, matched them to phonemes, assembled them into words, extracted meaning, and finally, delivered the meaning to your conscious awareness. The whole process took somewhere between 100 and 200 milliseconds. You're hearing the past. You're always hearing the past. You're seeing the past. Light takes time to reach your eyes. Not much time, At the distances we're talking about, the light from this page or this screen reaches you in nanoseconds, but the processing takes longer, 100 milliseconds from retina to conscious perception. Everything you see is at least a tenth of a second old by the time you become aware of it. You are feeling the past. When you touch something, a table, a hand, your own face, pressure sensors in your skin send signals up your spinal cord and into your brain. The journey takes time, 30 to 100 milliseconds, depending on where on your body the touch occurred. Your feet are farther from your brain than your face, and so a touch on your foot arrives later than a touch on your cheek. But you do not perceive this delay. Your brain compensates. It holds the signal from your cheek, waits for the signal from your foot to arrive, and then presents both sensations to you as though they occurred simultaneously. Your brain is editing your experience in real time, adjusting for the speed of nerve conduction so that your body feels unified and coherent instead of fragmented and delayed. You are living in a reconstruction, a simulation, a model of the world that your brain builds constantly from delayed and incomplete information. The brain does not show you reality. It shows you its best guess about reality, backfilled and smoothed and adjusted and compressed into a version that is simple enough, coherent enough, fast enough for you to act on. And here is the strangest part. You cannot escape this. You cannot perceive the present moment directly. You cannot see the world as it is right now. You can only see the world as it was a fraction of a second ago. The present is forever inaccessible. By the time you become aware of anything, it has already passed. The now you experience is not now. It is then. It is always then. William James called this the specious present, the felt duration of now, the span of time that feels, subjectively, like it is all happening at once. For most people, that span is about 2 to 3 seconds, not 1 second, not the precise cesium-defined second we've been examining. 2 to 3 seconds, a window, a moving window that slides forward through time, always centered on a moment that no longer exists. You're living in a delayed broadcast, and the delay is not optional. It is structural. It is the cost of consciousness. And yet, and this is the paradox, it is also where all meaning lives. Because the lag is not just a delay, it is a space in which the brain can edit, interpret, compress, and make sense of the flood of information arriving from the senses. Without the lag, you would be overwhelmed. You would perceive every photon, every air molecule, every vibration, every pressure change, every chemical signal, all at once, with no filtering, no prioritization, no meaning. You would drown in data. You would not experience anything at all, because experience is not the same as data. Experience is data plus interpretation, data plus memory, data plus context, data plus emotion. The lag is where that interpretation happens. The lag is where raw sensation becomes perception, where perception becomes experience, where experience becomes memory. The lag is where you become you. And so the second, the human second, the one you feel, the one you live inside of, is not the same as the cesium second. It is not the same as the second measured by atomic clocks in Boulder, Colorado. It is not the same as the second defined by 9 billion oscillations of a cesium atom. It is longer, slower, softer, more forgiving. It stretches backward in time, gathering up the recent past and presenting it to you as though it were the present. It is a fiction, a beautiful, necessary fiction. And it is the only second you will ever know. Let that settle. Feel the weight of it. You are not living in the present. You are living in the past, dressed up as the present. You are watching a recording, slightly delayed, edited for coherence, smoothed for continuity, and that recording is your life. Now let us leave the brain. Let us leave the human scale entirely. Let us follow something that does not lag, something that does not wait, something that moves at the only speed the universe considers absolute. Let us follow a photon. In exactly 1 second, light travels 299,792.458 kilometers. That number is not a measurement, it is a definition. Since 1983, the meter has been defined as the distance light travels in a vacuum in exactly 299,792,458th of a second. The speed of light is not measured anymore, it is fixed. It is the ruler by which all other distances are measured. 299,792 kilometers. Say it slowly. Let the number sit in your mind. It is large, but it is not unimaginable. It is roughly the distance you would travel if you drove around the Earth's equator 7.5 times. It is roughly the distance from the Earth to the Moon, minus about 85,000 kilometers. The Moon is 384,400 kilometers away on average. Light covers that distance in 1.28 seconds, a little more than 1 second. 1 second takes you most of the way there, but not quite all the way. Imagine this photon. Imagine you could mark it, tag it, follow it. It is not different from any other photon. It has no color by itself, no temperature, no size, not in the way we usually mean size. It is a quantum of light, a packet of electromagnetic energy, a ripple in the field. It travels at the speed of light because it is light. It cannot travel slower, it cannot travel faster. It moves at c's, and yas is the only speed it knows. Where did this photon come from? It was born in the core of the Sun, deep inside where the temperature is 15 million degrees Celsius and the pressure is 250 billion times the pressure at Earth's surface. Down there, in that furnace, hydrogen nuclei collide and fuse into helium, releasing energy in the form of gamma-ray photons, high-energy, short-wavelength packets of light. But those photons do not escape, not immediately. The core of the Sun is dense, unimaginably dense, roughly 150 grams per cubic centimetre, 10 times the density of gold. A photon born in the core collides with a particle of plasma almost immediately. It is absorbed, re-emitted, absorbed again, scattered, redirected. It bounces, again and again, trillions of times. It does not travel in a straight line. It wanders, a random walk through a sea of plasma. And this takes time, a very long time. Estimates vary, but the consensus is that a photon born in the Sun's core takes somewhere between 100,000 and 170,000 years to reach the surface. 100,000 years. Not because the distance is large and the Sun's radius is only 700,000 kilometers, but because the path is so convoluted. The photon is scattered so many times that its effective speed, its net outward progress, is only a few centimeters per hour. It drifts outward, slowly, randomly, over millennia. But eventually it reaches the photosphere, the surface, the visible layer of the Sun, and there it is free. It escapes. It travels outward into empty space at the full speed of the light. No more collisions, no more scattering, just vacuum and distance and time. From the Sun's surface to Earth, the photon travels for 499 seconds, 8 minutes and 19 seconds. That is the average. The Earth's orbit is elliptical, so the distance varies. At perihelion, when Earth is closest to the Sun, light takes 490 seconds. At aphelion, when Earth is farthest, it takes 507 seconds, but on average, 499. Now focus on 1 second of that journey, one arbitrary second somewhere in the middle. The photon has already travelled for, say, 250 seconds. It is halfway between the Sun and the Earth. It is crossing empty space. There is nothing here, no air, no particles, no field strong enough to deflect it. Just distance, just time, just the photon moving. In this 1 second, the photon covers 299,792 kilometers, enough to loop around Earth 7.5 times, enough to nearly reach the Moon. And no observer will ever witness this leg of the journey directly. No instrument is pointed at this exact photon, at this exact moment. It is alone, anonymous, one quantum among uncountable trillions streaming outward from the Sun in all directions. This is what 1 second looks like for light. It is vast, it is empty, it is solitary, and yet light itself does not experience time. From the photon's perspective, if we can even use that word, the journey is instantaneous. Special relativity tells us that as you approach the speed of light, time dilates. It slows down, and at exactly the speed of light, time stops. A photon emitted from the Sun and absorbed by your retina 8 minutes later experiences 0 elapsed time. From its perspective, emission and absorption are the same event. The journey does not happen. There is no duration, no waiting, no crossing. But from our perspective, from the perspective of anything moving slower than light, the journey takes time. It takes 8 minutes and 19 seconds, and in each of those seconds, the photon crosses a distance so large that it defies human intuition. We call the moon close, we call the sun nearby. But light does not call them close. Light calls them distant. Reachable, yes, but not immediate. Not here. There is space between us and them. Real space. Crossable only at a speed we cannot reach. This is the loneliness of the speed of light. It is the universe's speed limit. Nothing with mass can reach it. Nothing can cross a vacuum faster. And so, light travels alone, always, forever, at a speed nothing else can match. The photon we are following will complete its journey. It will reach Earth. It will strike an atom in the upper atmosphere, or a molecule of water in the ocean, or a leaf in a forest, or a cell in someone's retina. And when it does, it will be absorbed, its energy will be transferred, its journey will end. And another photon, somewhere else, will begin the same journey, an endless relay, an unbroken stream. But here, in this 1 second, in this arbitrary stretch of empty space, the photon is alone, moving, crossing distance, marking time in the only way light knows how, by travelling. And yet light, for all its constancy, is not the fastest thing the universe does. There are objects in the cosmos that spin so rapidly that their surfaces approach the speed light takes 8 minutes to achieve. There are events so violent that they release, in 1 second, more energy than our sun will radiate across its entire 10 billion year lifetime. And there are places where time itself warps, where our chosen second stretches or compresses depending on where you stand, where gravity bends duration the way a lens bends light. We have traced 1 second through the human body, through the planet, through the mind's delayed reconstruction of reality, and through the solitary crossing of a photon in empty space. Now we step outward, past the familiar, into the extremes, into the regions where the universe demonstrates what 1 second can contain when physics is pushed to its limits. Let us begin with rotation. Picture a sphere roughly 20 kilometers across, 10 miles if you prefer, a city-sized ball. But this is not a city. This is not rock or metal or anything you have touched. This is a neutron star, the collapsed core of a massive star that exploded long ago, leaving behind a remnant so dense that a teaspoonful of its material would weigh as much as Mount Everest. The gravity at its surface is 200 billion times stronger than Earth's. Light itself is bent as it tries to escape. And this sphere is spinning, not slowly, not once per day, or once per hour. It completes a full rotation, 360 degrees, equator returning to its starting point, in less than 0.002 of a second. This is PSR J1748. Tuskufov. Aid, a pulsar, the fastest spinning object ever confirmed. It was found in 2004, identified by radio astronomers using the Robert C. Byrd Green Bank telescope in West Virginia, and confirmed months later after repeated observations ruled out instrument error or atmospheric noise. The observations were unambiguous. The pulsar sits within a globular cluster called Terzan 5, approximately 18,000 light-years away in the constellation Sagittarius. Terzan 5 is old, ancient, a dense swarm of hundreds of thousands of stars, many of them remnants, many of them paired in tight binary systems where one star feeds on the other. PSR Sakuri J74SD 24 is part of such a pair. It orbits a companion star, locked in a 26-hour dance. The companion eclipses the pulsar for roughly 40% of each orbit. During those hours, the radio signal vanishes. Then it returns, steady, unvarying, pulsing at a rate of 716 times per second. 716 rotations in 1 second. Let that settle. In the time it takes your heart to beat once, this object has spun around 716 times. In the time it takes you to blink, it has completed roughly 250 full rotations. The surface at its equator is moving at 70,000 kilometers per second, roughly 24% of the speed of light. 1/4. If the pulsar were any larger, if its radius exceeded 16 kilometers, the centrifugal force would tear it apart. Material at the equator would be flung into space, unable to hold on. But it does not tear. It holds. Because gravity at this scale is overwhelming. Because the neutron star's mass, roughly 1.5 times the Sun's, is compressed into a sphere the size of a small city. Because the matter here is not atoms with electron clouds and empty space between nuclei. It is neutrons, packed so tightly that they touch. And from this spinning surface, a beam of radio waves sweeps outward. The pulsar's magnetic field, trillions of times stronger than Earth's, funnels charged particles along its magnetic poles, and as those particles spiral and accelerate, they emit radiation. Radio waves, beamed outward in 2 narrow cones, one from each magnetic pole. The magnetic axis is tilted relative to the spin axis, so as the pulsar rotates, the beam sweeps across space like a lighthouse. Once every 1.4 milliseconds, the beam crosses Earth. We detect it. A pulse, regular, unvarying, a cosmic clock. In 1 second, we receive 716 pulses. Think about what that means. This object is a clock more precise than anything human beings built until the invention of atomic clocks in the 1950s. Pulsars were discovered in 1967 by Jocelyn Bell Burnell, then a graduate student at Cambridge, who noticed repeating signals in radio data that were so regular they were briefly considered as possible evidence of extraterrestrial intelligence. They were not. They were neutron stars, collapsed cores, spinning, broadcasting their rotation to anyone listening. PSR J1748 2446 AD is the fastest of them, not the only fast one. There are others spinning hundreds of times per second, but the fastest confirmed, and it has been spinning this way for millions of years, possibly billions. Neutron stars lose rotational energy slowly, very slowly. They are slowing down, but the process takes so long that the change is nearly imperceptible. This pulsar will still be spinning at 700 times per second long after every human being alive today is gone. Now step back. Think about scale. In 1 second, this object completes 716 full rotations. The photon we followed earlier travelled 299,000 kilometres. The pulsar's equator, in that same second, travels a cumulative distance of over 3 million kilometres as it wraps around itself again and again. Different motion, different scale, but the same duration. 1 second. And yet the pulsar is not the universe's most violent 1-second event. That distinction belongs to a supernova. On the night of February 23, 1987, astronomers in the southern hemisphere looked up and saw something new. A bright point of light in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, approximately 168,000 light-years away. The light had been travelling for 168,000 years. It left its source long before modern humans existed, and it arrived that night visible to the naked eye, the brightest supernova seen from Earth since 1604. It was designated SN 1987A, the explosion of a star. But the light, the visible light, was not the first signal to arrive. Hours before the supernova brightened in the night sky, 3 underground detectors, built to study proton decay and solar neutrinos, registered a brief, intense burst of particles. 11 neutrinos at Kamiokande 2 in Japan, 8 at the Irvine, Michigan Brookhaven detector in Ohio, 5 at the Baksan Observatory in the Soviet Union. The detections were simultaneous, a 13-second burst. Neutrinos, nearly massless particles that barely interact with matter, passing through the detectors, through the Earth, through everything, almost unnoticed. Almost. Those 24 neutrinos were the first direct evidence of a supernova's core collapse. They confirmed in real time what theory had predicted for decades, that when a massive star exhausts its nuclear fuel, its core collapses in less than a second, and the collapse releases an unimaginable flood of energy, almost all of it in the form of neutrinos. Let me give you the number. During the first second of SN 1987A's core collapse, the dying star released approximately 10 to the 46th joules of energy. That is one followed by 46 zeros in neutrinos alone in 1 second. To put that in perspective, our Sun, over its entire 10 billion year lifetime, will radiate roughly 10 to the 44th joules of energy in the form of light and heat. SN 1987A, in 1 second, released 100 times that amount, in neutrinos, not light, not heat, neutrinos. Particles so weakly interacting that trillions of them pass through your body every second from the Sun, and you never notice. But in that 1 second, the collapsing core of SN 1987A produced so many neutrinos, released at such energies that they carried away 99% of the explosion's total energy. The light we saw, the visible supernova, the expanding shell of gas and plasma, that was the remaining 1%, a rounding error. The real event was invisible, subatomic, a flood of neutrinos streaming outward in all directions, carrying the star's gravitational binding energy into the void, and we detected 24 of them, 24 out of an estimated 10 to the 58 neutrinos released in total. The odds of detecting even that many were infinitesimal. But it happened, and it confirmed once and for all that our models of stellar collapse were correct, that neutron stars form this way, that supernovae are not just explosions but transformations, the violent birth of something new from the death of something old. The progenitor star, the star that exploded, was catalogued as Angelique 69202, a blue supergiant, not a red giant, which surprised astronomers at the time because theory predicted that stars this massive would expand into red supergiants before collapsing. But Angelique 69202 was blue, hot, luminous, and it exploded anyway. The discrepancy led to refinements in stellar evolution models. We learned that stars in low metallicity environments, like the Large Magellanic Cloud, lose mass differently, and that changes their evolutionary path. But set that aside, focus on the first second, the moment when the core, no longer able to support itself against gravity, collapsed inward. The iron core, roughly the mass of the Sun, compressed from the size of Earth to the size of a city in less than 1 second. The collapse was so rapid, so violent, that it released more power than all the visible stars in the observable universe combined. For 1 second, SN 1987A outshone the universe, not in light, in neutrinos, in gravitational energy, in the sheer violence of matter being crushed into neutron degeneracy. And then it was over. The collapse halted. The core rebounded. A shockwave formed and propagated outward, blowing away the star's outer layers. The light we saw arrived hours later, after the shockwave reached the surface, but the neutrinos left immediately. They did not wait. They passed through the collapsing star as if it were not there. They crossed 168,000 light-years of space and arrived at Earth on February 23, 1987, just before dawn. 1 second of collapse, 1 second of unimaginable energy release, and we were watching. Now we arrive at the places where time itself bends. At the centre of our galaxy, 27,000 light-years away, sits an object called Sagittarius A. For decades, astronomers tracked the orbits of stars near the galactic centre and watched them move in elliptical paths around something invisible, something massive, something compact. The stars moved fast, ridiculously fast. One star, designated S2, orbits Sagittarius A every 16 years, reaching speeds of 5,000 kilometers per second at its closest approach. That is nearly 2% of the speed of light. For a star. The only explanation was a supermassive black hole. Not a stellar mass black hole, the remnant of a single collapsed star, a supermassive one, millions of times the Sun's mass, concentrated in a region smaller than our solar system. In 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A. Not the black hole itself, black holes do not emit light, but the glowing ring of superheated plasma orbiting just outside the event horizon. The ring is bright, 10 billion Kelvin, hotter than anything we can produce on Earth, and at the centre, a shadow, the black hole's silhouette, the region from which no light can escape. The event horizon of Sagittarius A is roughly 24 million kilometers across, 16 times the distance from Earth to the Sun, not large by cosmic standards, but unimaginably dense. 4.3 million solar masses concentrated inside that boundary, and time, near that boundary, does not flow the way it does here. General relativity tells us that gravity warps space-time. The stronger the gravity, the greater the warp. Near a black hole's event horizon, the warp becomes extreme. Time slows down. Not metaphorically, not perceptually, literally. A clock near the event horizon ticks more slowly than a clock far away. An observer watching from a safe distance would see an infalling object slow down as it approaches the horizon, moving slower and slower, its light red-shifting, fading but never quite crossing. From the infalling observer's perspective, they cross the horizon in finite time, but from the distant observer's perspective, they never cross. Time stretches toward infinity. Our chosen second, measured by a clock far from any strong gravitational field, is not the same duration everywhere. Near Sagittarius A, that second stretches. How much depends on how close you are. At the event horizon, from the perspective of a distant observer, 1 second becomes infinite. Time stops, but step back slightly. Move away from the horizon. Time flows again, but slowly. Very slowly. If you could hover just outside the event horizon of Sagittarius A, an impossible feat, requiring an engine capable of resisting the black hole's pull, and you stayed there for what felt like 1 second, then returned to Earth, you would find that years had passed here. Possibly decades. Possibly more. Gravity makes time elastic. We saw this effect directly on September 14th, 2015. At 9:45 UTC, 2 detectors, one in Livingston, Louisiana, the other in Hanford, Washington, registered a signal. A ripple, a distortion in space-time itself passing through the Earth, stretching and compressing the detector's arms by a distance far smaller than the width of a proton. The distortion lasted a fraction of a second, but it was unmistakable. The signal was designated GW150914, a gravitational wave, the first ever directly detected. The source was identified through careful analysis of the waveform. 2 black holes, roughly 36 and 29 solar masses, orbiting each other in a death spiral. They had been orbiting for millions of years, slowly losing energy to gravitational wave radiation, drawing closer and closer. And then, in the final moments, they merged. The merger itself took less than 1 second. In the final 0.2 of a second, the black holes circled each other dozens of times, accelerating, spiraling inward, their event horizons distorting and stretching and finally touching. And as they merged, they released 3 solar masses of energy, not in light, not in particles, in gravitational waves, ripples in space-time propagating outward at the speed of light. 3 solar masses, converted entirely into gravitational radiation in 0.2 of a second. The power output during those final moments was 50 times the combined luminosity of all the visible stars in the observable universe. For 0.2 of a second, this merger was the brightest event in the cosmos, not in visible light, in gravity. The gravitational waves travelled outward, crossing space, weakening as they spread. They crossed 1.3 billion light-years. They passed through galaxies, through voids, through clusters of stars, and they reached Earth on September 14th, 2015. They passed through the planet, through the detectors, through you, stretching and compressing space itself by an amount so small that detecting it required the most sensitive instruments ever built. The LIGO detectors are extraordinary pieces of engineering. Each consists of 2 arms, each 4 kilometers long, arranged in an L shape. A laser beam is split and sent down each arm, reflected back by mirrors, and recombined. When the arms are exactly the same length, the beams interfere destructively and cancel out. But when a gravitational wave passes through, it stretches one arm and compresses the other, changing the interference pattern. The change in length is minuscule, smaller than the diameter of a proton, but it is measurable. GW150914 changed the length of LIGO's arms by roughly 1/10,000th the width of a proton, and both detectors, separated by 3,000 kilometers, registered the same signal within 7 milliseconds of each other. The probability of this being a coincidence, an accidental fluctuation in detector noise, was calculated at less than 1 event per 203,000 years. The statistical significance was greater than 5 sigma. It was real, and it told us definitively that Einstein was right. That general relativity's prediction of gravitational waves made in 1915 was correct. That space-time is not a static stage on which events occur, but a dynamic fabric that ripples and bends and stretches in response to mass and energy. It also told us that black holes merge, that they exist in binary systems, that they spiral inward over vast timescales, radiating gravitational energy until they collide. And when they collide, they release more power, in a fraction of a second, than every star we can see combined. 1 second, or a fraction of it, contains all of this: the fastest rotation, the most violent collapse, the most extreme warping of time. These are not hypothetical limits. These are measured events, observed phenomena, things that happened or are happening in the universe we inhabit. The pulsar spins, the supernova collapses, the black holes merge, and in each case, the universe demonstrates that 1 second, the same second we use to mark our heartbeat and measure our coffee and count the delay before speaking, is also the duration in which the cosmos performs its most staggering acts. Time is not the same everywhere. 1 second near a black hole is not the same as 1 second here. 1 second in the frame of a photon does not exist at all. 1 second for a pulsar is 716 rotations. 1 second for a collapsing star is the release of more energy than a star radiates in 10 billion years. The second is a container, universal, but its contents and its subjective length depend entirely on where you stand and what you are witnessing, and we are only beginning. We turn now to the larger scale, pull back from the colliding black holes, from the spinning pulsars, from the exploding stars, pull back past galaxies, past clusters, past the filaments of matter that thread through the dark. Pull back until you can see the whole observable universe at once, a sphere of space roughly 93 billion light-years in diameter, filled with 2 trillion galaxies, each containing hundreds of billions of stars, all of it suspended in an expanding void. The universe is not still. It never has been. And in this second, the 1 second we have been tracing from your heartbeat to the edge of physics, the entire observable universe is expanding. The expansion is silent. It produces no sound, no light, no vibration you could ever feel. It does not push galaxies apart the way an explosion would. It does not fling matter through space. Instead, space itself stretches. The fabric of the universe, the 4-dimensional geometry described by Einstein's equations, is growing, and every point in it is moving away from every other point, not because they are travelling, but because the distance between them is increasing. The rate of this expansion is described by the Hubble constant, a number that tells you how fast a galaxy is receding based on how far away it is. The current value is approximately 70 kilometers per second per megaparsec. A megaparsec is roughly 3.3 million light-years. So if a galaxy is 1 megaparsec away from us, it is receding at 70 kilometers per second. If it is 2 megaparsecs away, it is receding at 140 kilometers per second. The farther away something is, the faster it moves away from you. In 1 second, a galaxy 1 megaparsec distant recedes by 70 kilometers. That is the length of a medium-sized city, added to the emptiness between us and it, in the time it takes your heart to beat once. Now consider a galaxy much farther out. At a distance of roughly 14 billion light-years, the Hubble radius, galaxies are receding from us at the speed of light. In 1 second, the space between us and them grows by 299,792 kilometers. They are not moving through space at that speed. Space itself is expanding at that rate. And beyond that radius, galaxies are receding faster than light. Not because they are breaking the cosmic speed limit, but because the limit applies only to motion through space, not to the expansion of space itself. This means there are galaxies we will never see. Light that left them billions of years ago is travelling toward us, but the space between us and them is expanding faster than the light can cross it. The photons are running on a treadmill that is accelerating away from them. They will never arrive. The universe contains regions that are and will remain forever beyond our view. And in this second, that boundary is moving. The edge of the observable universe is not fixed. It is a horizon, receding as light from more distant objects finally reaches us. But the expansion is accelerating, driven by something we call dark energy, a term that means we do not know what it is. The rate of expansion is increasing. Galaxies that are visible now will eventually cross the Hubble radius and disappear from view, their light redshifted into invisibility, their images frozen at the edge of the observable universe, fading slowly into the dark. The expansion is everywhere. It is not centered on any one point. Every observer in every galaxy sees the same thing, everything else moving away from them. The universe has no center, or rather, every point is the center. The Big Bang did not happen at a location. It happened everywhere at once, and the universe has been expanding from that everywhere ever since. In this second, as you sit or stand or lie still, the space around you is stretching, not noticeably. The effect is only measurable over vast distances, far larger than galaxies. The Milky Way is not expanding. The solar system is not expanding. The atoms in your body are not expanding. Gravity and the other fundamental forces hold those structures together. But the voids between galaxy clusters, those immense stretches of near-empty space, are growing. And in this second, they grow by billions of kilometers. The universe is also filled with light. Ancient light. The oldest light we can see. In 1964, two radio astronomers working at Bell Telephone Laboratories in Holmdel, New Jersey, detected something they did not expect. Arno Penzias and Robert Wilson were using a 20-foot horn reflector antenna, originally built for satellite communication, to measure radio emissions from the Milky Way. But no matter where they pointed the antenna, they heard the same faint hiss. A background noise, uniform in all directions, persistent and inexplicable. They checked the equipment. They cleaned the antenna. They removed a pair of pigeons that had nested inside and scrubbed away the droppings. They recalibrated the instruments. The hiss remained. It was not coming from the galaxy. It was not coming from the sun. It was coming from everywhere at once. They had discovered the cosmic microwave background, the afterglow of the Big Bang. The universe, in its earliest moments, was unimaginably hot and dense. Matter and energy were so tightly packed that photons could not travel freely. They were constantly absorbed and re-emitted by the surrounding particles. The universe was opaque, a glowing fog, but as it expanded, it cooled, and roughly 380,000 years after the Big Bang, the temperature dropped enough for protons and electrons to combine into neutral hydrogen atoms. The fog cleared, photons were suddenly free to travel. They have been travelling ever since. Those photons, emitted when the universe was a tiny fraction of its current size, have been stretched by the expansion of space. They began as visible and ultraviolet light. 13.8 billion years later, they have been redshifted into microwaves. Their temperature, once thousands of degrees, is now 2.7 Kelvin, just above absolute zero. But they are still here, still passing through everything, still carrying the imprint of the universe as it was in its infancy. In this second, those ancient photons are washing through your body. Billions of them. They pass through the walls, through the air, through your skin and bones. They are the oldest thing you will ever touch. Older than the Earth. Older than the Sun. Older than any star. They have been travelling for longer than anything else in the universe has existed, and they are still moving, filling every corner of space with the faint uniform glow of a fire that went out 13 billion years ago. Penzias and Wilson did not initially understand what they had found. It was only after consulting with physicists at Princeton, who had been developing the theoretical framework for detecting the Big Bang's remnant radiation, that the significance became clear. In 1978, Penzias and Wilson were awarded the Nobel Prize in Physics. The horn antenna they used still stands in New Jersey, a monument to one of the most important discoveries in the history of cosmology. The cosmic microwave background is not perfectly uniform. It contains tiny fluctuations, variations in temperature of only a few millionths of a degree. Those fluctuations are the seeds of structure. Slightly denser regions in the early universe attracted more matter. Over billions of years, those regions collapsed under their own gravity, forming the first stars, the first galaxies, the clusters and superclusters, and filaments we see today. The cosmic microwave background is a snapshot of the universe before any of that existed. Before stars, before galaxies, before structure. It is the earliest image we have, and it is still here, still drifting through space, still carrying the pattern of everything that would come after. In this second, the universe expands, the ancient photons drift, the largest motions in the cosmos unfold in silence. Now we turn inward, sharply inward, not to stars or atoms, but to something in between, to the molecular machinery that powers every living thing. Inside your body, embedded in the inner membrane of every mitochondrion in every cell, are thousands of tiny rotary engines. They are called ATP synthase. Each one is a molecular motor, a structure made of protein subunits arranged in two main parts, a rotor and a catalytic head. The rotor is embedded in the membrane. The catalytic head sits above it, attached by a central stalk. Protons, hydrogen ions, flow through the membrane driven by a concentration gradient, and as they pass through the rotor, they force it to spin. The rotation is transmitted to the catalytic head, which uses the mechanical energy to synthesize ATP, adenosine triphosphate, the molecule that stores chemical energy in all living cells. ATP synthase was isolated in 1960 by American biochemist Ephraim Racker. The mechanism, the fact that it rotates, was proposed in 1974 by Paul Boyer and confirmed in 1994 by John Walker using X-ray crystallography. Both shared the 1997 Nobel Prize in Chemistry for this work. The motor spins at up to 9,000 revolutions per minute. That is 150 rotations per second. And with each rotation, the catalytic head produces roughly 3 molecules of ATP. So a single ATP synthase enzyme, in 1 second, produces approximately 100 ATP molecules. You have thousands of these motors in a single cell, and you have trillions of cells. In 1 second, your body produces and consumes an incomprehensible number of ATP molecules. Over the course of a day, you synthesize roughly your own body weight in ATP. It is created, used, and recycled continuously. ATP is the universal currency of energy. Discovered in 1929 by German chemist Carl Lohmann and identified as the primary energy carrier by Fritz Lipmann, in the early 1940s, it powers nearly every biological process: muscle contraction, nerve signaling, protein synthesis, cell division, transport of molecules across membranes. Without it, you would die in minutes. If ATP production were to stop entirely, your existing stores would be depleted in roughly 4 minutes. ATP synthase is one of the most efficient molecular machines known. It operates at near 100% efficiency, converting the energy of the proton gradient almost entirely into chemical energy stored in ATP. It is a nanometer-scale turbine, smaller than any machine we have ever built, and it runs continuously, day and night, from the moment you are born until the moment you die. In this second, billions of these motors are spinning inside you. Now press deeper still, into the leaf of a plant, into the chloroplasts where photosynthesis occurs. A photon, a particle of light, strikes a chlorophyll molecule embedded in the thylakoid membrane. The molecule absorbs the photon. An electron is excited to a higher energy state. That electron is transferred to a nearby molecule, beginning a cascade of reactions that will eventually produce glucose and oxygen. The initial absorption, the moment the photon is captured and the electron is promoted, takes approximately 300 femtoseconds. That is 3 times 10 to the negative 13 seconds, 3/10 of a trillionth of a second. In the time it takes you to blink, roughly 150 milliseconds, that absorption event happens 500 trillion times in a single leaf. Now deeper, to the bonds between atoms. A carbon-carbon covalent bond, the kind that holds organic molecules together, vibrates. The atoms do not sit still. They oscillate, stretching and compressing, at a frequency of roughly 10 to the 13th hertz, 10 trillion times per second. In 1 second, the bond completes 10 trillion cycles. Every molecule in your body is vibrating at this frequency. Your skin, your bones, your eyes, the proteins in your blood, all of it is humming, invisibly, at rates far faster than any motion you can perceive. The molecular world is not still. It is not calm. It is a continuous blur of motion, rotation, vibration, and exchange. Energy flows through it in torrents. Electrons jump, protons flow, motors spin, bonds vibrate, all of it happening faster than thought, faster than perception, faster than any conscious process, and yet it is not random. It is structured, regulated, tuned. Evolution has built machines at the molecular level that rival anything we have ever engineered. They are more efficient, more precise, and vastly smaller, and they run, without pause, in every living thing. In 1 second, they complete billions of cycles, each cycle a transaction, each transaction necessary. This is the machinery of life. This is what keeps you alive. Now deeper still, below the molecules, below the atoms, into the subatomic. Every second, roughly 65 billion solar neutrinos pass through every square centimeter of your body, day and night. Whether you are indoors or outdoors, whether it is noon or midnight, the neutrinos do not stop. They are produced in the core of the sun, where hydrogen nuclei fuse into helium under temperatures of 15 million degrees and pressures 250 billion times that of Earth's atmosphere. The fusion reactions release neutrinos, trillions upon trillions of them, streaming outward in all directions at nearly the speed of light. Neutrinos barely interact with matter. They have no electric charge. They have almost no mass. They pass through the Earth as if it were not there. In 1 second, 65 billion of them pass through a patch of your skin the size of your thumbnail. Most pass straight through. A handful might scatter off a nucleus in your body, but the odds of a neutrino interacting with you at all, in your entire lifetime, are vanishingly small. They are ghosts, invisible, intangible, almost undetectable. The existence of the solar neutrino flux was predicted theoretically in the 1960s by physicist John Barkhall. He calculated, based on models of the Sun's interior, how many neutrinos should be reaching Earth. But when experiments were conducted to detect them, they found only about 1/3 of the expected number. This became known as the solar neutrino problem. It persisted for decades. The discrepancy suggested either that our models of the Sun were wrong, or that something about neutrinos themselves was not understood. The answer came from the Sudbury Neutrino Observatory in Ontario, Canada. The detector was located 2,100 meters underground in a nickel mine, shielded from cosmic rays and other background radiation. It contained 1,000 tons of heavy water made with deuterium instead of ordinary hydrogen, surrounded by photomultiplier tubes that could detect the faint flashes of light produced when neutrinos interacted with the heavy water. The Sudbury Neutrino Observatory confirmed that the total number of neutrinos reaching Earth matched Barkhall's predictions. But it also showed that neutrinos change flavor as they travel. They oscillate between 3 types: electron neutrinos, muon neutrinos, and tau neutrinos. The earlier experiments had only been sensitive to electron neutrinos. By the time the solar neutrinos reached Earth, many had oscillated into other flavors. The Sun was producing exactly the number of neutrinos predicted. We had simply been looking for the wrong kind. Arthur MacDonald, the director of the Sudbury Neutrino Observatory, was awarded the Nobel Prize in Physics in 2015 for this discovery. In this second, those neutrinos continue to pass through you. Unseen, unfelt, a constant rain of particles from the Sun, travelling through everything, leaving almost no trace. Now consider the Large Hadron Collider, the particle accelerator beneath the border of France and Switzerland, operated by CERN, the European Organisation for Nuclear Research. The collider is a ring 27 kilometers in circumference. Inside it, protons are accelerated to 99.9999991% of the speed of light. At that speed, time dilation becomes significant. From the proton's reference frame, the ring is contracted to a tiny fraction of its actual length. From our reference frame, the protons are completing 11,245 circuits of the ring per second. In 1 second, a single proton travels more than 300,000 kilometers. That is 75% of the distance from the Earth to the Moon. The beams contain trillions of protons. When they collide at full intensity, the Large Hadron Collider facilitates up to 600 million proton collisions per second. Each collision releases a burst of energy, creating showers of new particles that exist for fractions of a second before decaying into other particles, which decay into others, until finally only stable particles remain: protons, neutrons, electrons, photons, neutrinos. The energy in a single proton beam at full power is 315 megajoules. That is roughly the kinetic energy of a 1-ton elephant running at 50 kilometers per hour, concentrated into a beam thinner than a human hair. If that beam were to be accidentally released, it would bore through the tunnel wall, vaporizing everything in its path. The collider operates at temperatures colder than outer space. The superconducting magnets that steer the beams are cooled to negative 271.3 degrees Celsius, just a few degrees above absolute zero. The interior of the beam pipe is one of the coldest extended regions in the known universe, and inside that frozen tunnel, protons race at nearly the speed of light, colliding 600 million times per second, creating conditions that have not existed in the universe since the first moments after the Big Bang. The collisions probe the structure of matter. They test the predictions of the standard model of particle physics. They search for new particles, new forces, new symmetries. In 2012, the Large Hadron Collider discovered the Higgs boson, the particle associated with the field that gives other particles mass. The discovery confirmed a prediction made in 1964. It completed the Standard Model, and it earned Peter Higgs and François Englert the Nobel Prize in Physics in 2013. But the collisions also reveal something deeper. They show us that matter, at its most fundamental level, is not made of solid particles sitting still. It is made of fields, constantly fluctuating, exchanging quanta, interacting through forces mediated by other particles that exist for only the briefest instants. Inside a proton, quarks are bound together by the strong nuclear force. The force is carried by particles called gluons. Quarks and gluons exchange constantly. A quark emits a gluon, which is absorbed by another quark. The process happens over and over, billions of times per second. The gluons do not travel far. They are confined within the proton, bound by the same force they carry, but they are real. They exist. They can be detected indirectly in high-energy collisions. The weak nuclear force, which governs certain types of radioactive decay, is carried by particles called W and Z bosons. These particles are heavy, roughly 80 times the mass of a proton, and they are short-lived. A W or Z boson exists for approximately 3 times 10 to the negative 25 seconds before decaying into other particles. That is 3/10 septillionths of a second. Shorter than any interval we have discussed so far, shorter than the vibration of a bond, shorter than the oscillation of light, shorter than anything that can be measured directly. The bosons are never observed directly. They are inferred from their decay products, an electron and a positron, or a muon and an antimuon appearing suddenly in a detector. The signature of a particle that existed for an instant too brief to measure and then was gone. The subatomic world is not a collection of objects. It is a storm, a continuous exchange of particles and energy, governed by quantum fields that permeate all of space. Every interaction involves the creation and annihilation of particles. Virtual particles flicker in and out of existence, borrowing energy from the vacuum for timescales so short that the uncertainty principle permits it. The vacuum itself is not empty. It seethes with activity, fluctuations occurring at scales far too small and too fast for us to perceive, but real nonetheless, measurable in their effects on atoms and particles. In 1 second, quarks exchange gluons trillions upon trillions of times. Electrons emit and absorb virtual photons. Neutrinos pass through matter almost unimpeded. Protons race around a 27-kilometer ring 11,000 times. W and Z bosons flicker into existence and decay in intervals shorter than any clock can measure. The second is not a pause. It is not a moment of stillness. It is a container for more motion, more events, more transactions than the human mind can hold. From the expansion of the universe to the vibration of a bond, from the drift of ancient photons to the spin of molecular motors, from the collision of protons to the passage of neutrinos, the second contains scales of activity that span more than 40 orders of magnitude. And we are not done. There are faster events still, smaller scales, briefer durations. The second, as we have defined it, is not the limit. It is only a marker. A unit we chose because it aligns roughly with the rhythm of a human heart. But the universe does not stop at the second. It continues, down into intervals so brief that language begins to fail. We will go there next. We have reached femtoseconds, quadrillionths of a second. 1 second contains 1,000 trillion femtoseconds. At this scale, light crosses the width of a virus. A chemical bond vibrates once. An electron begins to move within a molecule, responding to the electromagnetic force, shifting its position in the cloud of probability that surrounds an atomic nucleus. This is the realm of attosecond science. Attoseconds are 1,000 times shorter than femtoseconds. 1 attosecond is 1 quintillionth of a second. 1 second contains a quintillion of them, a billion billions. The number is almost impossible to hold. If you tried to count attoseconds, 1 per second, it would take you 30 billion years, twice the age of the universe. At this scale, individual electrons move. Not the vibration of a bond, but the motion of a single electron within an atom, responding to the arrival of a photon, jumping from one orbital to another, or being torn free entirely in a process called ionization. For most of the history of physics, this motion was invisible. It happened too quickly to observe. electrons were studied statistically in populations through the averages of countless interactions. But the motion itself, the trajectory of a single electron over a few hundred attoseconds, remained beyond reach. That changed in 2001. In that year, Pierre Agostini, working at a laboratory in France, produced a train of light pulses, each lasting 250 attoseconds. The pulses were generated by focusing an intense infrared laser into a chamber of noble gas, neon or argon, and allowing the light to interact with the atoms in a way that produced harmonics, overtones of the original frequency, stacked together into bursts of extreme ultraviolet light. The bursts arrived in rapid succession, like the ticking of a clock running a quintillion times per second. In the same year, Ferenc Krauss, working in Austria, isolated a single pulse. Not a train, but one flash. It lasted 650 attoseconds. That pulse represented the shortest controlled event in the history of measurement. It was brief enough to capture the motion of an electron as it left an atom. The work built on foundations laid nearly 15 years earlier. In 1987, Anne Lehouillier, then a young researcher, discovered that when infrared laser light passed through a noble gas, it did not simply scatter. It produced overtones, higher frequencies of light, harmonics of the original beam, stacked in a pattern that suggested something strange was happening inside the atoms. The electrons were being driven by the oscillating electric field of the laser, accelerating and then snapping back, emitting bursts of light at each return. The overtones were the signature of that motion. The finding was unexpected. It opened a pathway. 16 years later, in 2003, the pathway became a tool. Agostini, Krauss and Lehouillier shared the Nobel Prize in Physics in 2023 for their experimental methods that generated attosecond pulses of light for the study of electron dynamics in matter. The citation noted that the work had opened the door to a timescale previously inaccessible to observation. It had, in the words of the Nobel Committee, opened the door to the world of electrons. The applications are numerous. Attosecond pulses can track the ionization of an atom in real time, watching as an electron absorbs energy and breaks free from the nucleus. They can observe the movement of charge within a molecule during a chemical reaction. They can measure the delay between the moment a photon strikes an atom and the moment an electron responds. That delay is not instantaneous. It takes time, tens or hundreds of attoseconds, for the electron to react. The lag can be measured now, it can be mapped. This is not abstract. Electrons govern the behavior of matter. Chemical bonds form and break because electrons move. Light is absorbed or reflected because electrons respond to electromagnetic fields. Conductivity, magnetism, color, the structure of solids, all of it depends on the motion of electrons at attosecond timescales. To observe that motion is to see the machinery of the material world. But attoseconds are not the limit. Quantum electrodynamics, the theory that describes the interaction of light and matter, predicts that the vacuum itself is active. Empty space, far from being empty, is filled with fluctuations. Virtual particles appear and disappear, borrowing energy from the quantum field for intervals so brief that the uncertainty principle permits their existence without violating the conservation of energy. An electron and a positron flicker into being, exist for a moment, and annihilate. The interval is shorter than an attosecond. It is measured in zeptoseconds. 1 zeptosecond is 10 to the negative 21 seconds, 1,000 times shorter than an attosecond, 1 billion trillion times shorter than a second. At this scale, the vacuum seethes. Particle pairs form and vanish. The process is continuous, occurring everywhere at all times. The particles are called virtual because they cannot be observed directly. They exist for intervals too short to measure, but their effects are real. They contribute to the mass and charge of electrons. They alter the energy levels of atoms in ways that can be detected with extraordinary precision. The Lamb shift, discovered in 1947, is one such effect. It is a tiny splitting of energy levels in hydrogen, caused by the interaction of the electron with virtual photons in the vacuum. The measurement confirmed a prediction of quantum electrodynamics and earned Willis Lamb the Nobel Prize. The vacuum is not a backdrop. It is an actor. It participates in every interaction, and it operates on timescales that approach the edge of what can be described. That edge is the Planck time. The Planck time is 5.39 times 10 to the negative 44 seconds. It is the smallest interval of time that has meaning within our current understanding of physics. It is not a measured quantity. It is derived, calculated from the speed of light, the gravitational constant, and Planck's constant. It represents the duration it would take a photon, travelling at the speed of light, to cross one Planck length, which is approximately 1.62 times 10 to the negative 35 meters. That length is unimaginably small, far smaller than an atom, smaller than a nucleus, smaller than a quark. It is the scale at which the smooth geometry of space-time, as described by general relativity, is expected to break down entirely. 1 second contains approximately 1.855 times 10 to the 43 Planck times. That is nearly 200 million trillion Planck intervals in every second. The number is so large that it loses intuitive meaning, but it tells us something important. It tells us that the second, our second, the second we defined in Paris in 1967, the second we measure with cesium clocks, contains within it an almost incomprehensible depth of structure. The second is not smooth, it is not continuous. At the deepest level, it may be composed of discrete indivisible units, ticking forward in steps too small to observe, but real nonetheless. This is the hypothesis of loop quantum gravity. The theory, developed by physicists including Lee Smolin, Carlo Rovelli and others, proposes that space-time is not a continuous fabric, but a network of finite loops, woven together into a structure that, at large scales, appears smooth, but at the Planck scale reveals itself to be granular. Space is quantized. Time is quantized. There is no such thing as an infinitely small interval. There is no such thing as a point with zero size. The universe, at its foundation, is discrete. If this is correct, and it remains a hypothesis, untested, because the Planck scale lies far beyond the reach of any experiment we can currently perform, then the second is not a continuum. It is a sequence, a chain of Planck time steps, linked together, each one representing the smallest possible change in the state of the universe. Below that scale, the question what happens next has no meaning. There is no next. There is only the network, the loops, the geometry of space-time itself, flickering between configurations in intervals that are by definition the limit of time. We do not know if this is true. We do not know if space-time is smooth or granular, continuous or discrete. The equations of general relativity assume smoothness. The principles of quantum mechanics suggest discreteness. The two frameworks do not agree. At the Planck scale, they both fail. General relativity predicts singularities, points where density and curvature become infinite. Quantum mechanics forbids infinities. Something has to give. A theory of quantum gravity is needed, and we do not have one yet. We have candidates. Loop quantum gravity is one. String theory is another. Others exist, but none has been confirmed. So we stand at the edge. We can describe the universe down to zeptoseconds, perhaps shorter. We can infer the behavior of virtual particles, the fluctuations of the vacuum, the motion of quarks within protons. We can measure the oscillation of cesium atoms with precision accurate to 1 second in 300 million years. But below the Planck scale, we are blind. The mathematics dissolves. The concepts stop working. We reach the boundary of the knowable, and yet the universe continues. Whatever happens at the Planck scale happens. The fields fluctuate. The loops connect. The quantum foam, if that is what it is, seethes and shifts. The second ticks forward, 1 Planck time at a time, or smoothly, or in some other way we have not imagined. It does not wait for us to understand it. Let that sit with you. 1 second. 9 billion cesium oscillations, a quintillion attoseconds, 200 million trillion Planck times. The number is so large that it ceases to convey anything. But the reality it points to is this. The second is not a simple unit. It is not a pause, not a gap, not a container. It is a layered, nested, fractal structure of events occurring at every scale simultaneously, from the expansion of space-time itself down to the Planck scale flicker of quantum geometry. And all of it happens at once, in the same second. The same 9 billion oscillations, Sagittarius A warps the fabric of space-time around it, bending light and time into spirals that tighten as they approach the event horizon. The black hole spins, dragging space itself into rotation, creating a region where nothing can stand still, where every particle, every photon, every field is pulled into the current. The warping is not metaphorical, it is geometric. The black hole does not exert a force, it curves the stage on which motion occurs. In the same second, PSR J1748 2446 AAD completes 716 rotations. Its surface, moving at nearly a quarter of the speed of light, does not tear apart because the neutron star's gravity is so intense that nothing can escape. The magnetic field, 1 trillion times stronger than Earth's, channels particles into beams that sweep across space like the beam of a lighthouse. Each sweep is a pulse. Each pulse marks one rotation, 716 times per second. In the same second, the Sun converts 4 million tons of its own mass into light. The mass does not disappear. It becomes energy, radiated outward in all directions, traveling at the speed of light, carrying the heat and illumination that make life on Earth possible. The conversion is governed by Einstein's equation, E equals mc squared. Mass and energy are equivalent. The Sun burns its own substance to shine. In the same second, lightning strikes the Earth 100 times. Each bolt releases energy equivalent to a small bomb. The temperature in the channel exceeds 30,000 degrees. The air is ionized. The sound is thunder. The light is visible for miles. 100 bolts scattered across the planet over oceans and forests and plains, each one a discharge of electrical potential, built up by the motion of water droplets in storm clouds. In the same second somewhere, a heart beats. The sinoatrial node fires. The electrical impulse spreads across the atria, then down through the ventricles. The chambers contract. Blood is pushed forward. Diastole follows. The chambers refill. The cycle repeats. 1 beat, 0.8 seconds on average. Slightly more than 1 beat per second for a heart at rest. The rhythm is autonomous. It does not require thought. It continues, second after second, for a lifetime. In the same second, an enzyme spins. ATP synthase, embedded in the inner membrane of a mitochondrion, rotates at approximately 150 times per second, driven by a flow of protons. Each rotation produces 3 molecules of ATP. The energy is stored in a chemical bond, ready to be released when the cell needs it. The enzyme is a machine. It has moving parts. It converts potential energy into chemical energy with remarkable efficiency. In the same second, 65 billion neutrinos pass through your thumbnail. They come from the Sun. They were produced in the core, in the fusion reactions that power the star. They travelled outward, through the radiative zone, through the convective zone, through the photosphere, and then across space to Earth. They do not slow down. They do not stop. They pass through the planet as if it were not there. Most of them pass through you without interacting. A few, very few, will collide with a nucleus in your body. The probability is low, but it is not zero. In the same second, a virtual particle pair appears, an electron and a positron flickering into existence in the vacuum, borrowing energy for an interval of 4 times 10 to the negative 21 seconds. They exist. They interact briefly with the fields around them. Then they annihilate, returning the borrowed energy, vanishing as suddenly as they appeared. The process is not rare. It happens everywhere, constantly, at every point in space. The vacuum is never still. All of this, every scale, every event, every oscillation and rotation and emission and interaction, occurs within the same second. The same 9,192,631,770 oscillations of a cesium atom. The second does not choose, it does not prioritize. It is not a spotlight that illuminates one scale at a time. It is a stage on which the entire universe performs, simultaneously at every level from the cosmological to the quantum. The second is not a container you fill with events. It is a symphony in which every instrument plays at once. The melody is not separate from the harmony. The rhythm is not separate from the tone. You cannot hear one part without the others. The music is the whole. The second is the whole, and it has no preference for your scale. The second does not care that you perceive it as the gap between 2 heartbeats, or the interval during which you register a decision your brain made half a second earlier. It does not care that a photon from its own reference frame experiences no time at all. It does not care that a pulsar spins 700 times, or that a virtual particle exists for a trillionth of a second. All of it is the second. All of it happens. All of it is real. You are living at one scale. Your perception is tuned to durations of a few hundred milliseconds. You experience the present as a window, roughly 2 to 3 seconds wide, within which events seem to occur now. But now is not a point. It is a construct, built by your brain from delayed signals, edited for coherence, presented to your conscious mind as a unified experience. The now you perceive is already past. The events you think are happening now have already happened, and your brain is only just catching up. But the second itself does not lag. It does not delay. It unfolds everywhere, at every scale, in perfect synchrony. The oscillation of the cesium atom, the rotation of the pulsar, the emission of the photon, the vibration of the bond, the flicker of the virtual particle, all simultaneous, all occurring within the same interval. The second is universal. It is shared. This is the resolution. Not an answer, but a reframe. A second is not a unit of time in the way you might think. It is not a box or a segment or a gap between moments. It is a bandwidth, a spectrum, a range of phenomena stacked and nested and interlaced, all happening at once, all contained within the same definition, the same 9 billion oscillations, but expressing themselves at scales that span more than 40 orders of magnitude. From the Planck time to the second itself, from the quantum foam to the drift of galaxies, the universe does not choose one scale and ignore the others. It plays them all. It performs them all. It is all of them, simultaneously without contradiction. The second is where it all happens. Not sequentially, not in stages, all at once. The second just ended. Another has already begun, and in this new second the same symphony plays again. Sagittarius A warps spacetime. PSR J-Can-748. 2PM446 AD spins 716 times. The sun converts mass into light. Lightning strikes. A heart beats. An enzyme rotates. Neutrinos pass through. A virtual particle flickers. 9 billion oscillations of a cesium atom mark the interval from beginning to end. You are inside it. You are made of it. The atoms in your body were forged in stars. The electrons in those atoms are moving right now at attosecond timescales. The bonds vibrating. The enzymes spinning, the neutrinos passing through, the quarks exchanging gluons, the fields fluctuating. You are not separate from the second. You are part of the performance, and the second does not end. It repeats, it continues, it unfolds one after another in an unbroken chain that stretches from the beginning of time to whatever lies ahead. Each second contains the whole universe, every scale, every event, every breath, every heartbeat, every oscillation, every flicker of light. The second is not small, it is vast. It is not simple, it is infinitely complex. It is not a pause, it is motion at every level, all at once. Let it carry you.